Now we have the next speaker. I think it's Rajesh Gopakumar. Where's Rajesh? And Rajesh is talking about simplifying string theory.
So, maybe this is okay. Yeah, you can maybe give me that. Yeah. Yeah, in the meanwhile. This inaugural day has finally arrived. I mean, being at ICTS myself, I've seen at close quarters the sort of the Herculean efforts involved in bringing ICTS to this stage, and Spenta and Avinash and the whole ICTS staff, and with the larger support, of course, of the engineers, the workers, and everything. It's been quite awe-inspiring to see it sort of come together. So it's really brick by brick building the institution. But as the spirit of this meeting, so now on to the science, right? I mean, so simplifying string theory. Well, string theory, I mean, I hope not in the present audience, but at least in general, this thing has a reputation for being an esoteric and mathematical discipline, and present company excluded, many people presume it's divorced from reality. So what's the big question that string theorists face? So at least this is one of the questions I face. So how many dimensions do you live in these days? 10, 11, 26, and so on. So of course we are an easy target for amusement, and okay. But my task today will be to try to to give you a sort of a glimpse of how ideas originating from string theory, and in fact, towards the end, I'll show how it's sort of feeding back to string theory. Feeding back into string theory, it's better. Into string theory, give new insight into certain 2- or 3-dimensional systems. Now, of course, if you're very chauvinistic about your 4-dimensional world, that may not be good enough, but I can just tell you to just temporarily to sort of ward off the skepticism. There's at least of potential interest in statistical physics and condensed matter systems. And some of the systems we'll consider do have a role to play there, but the main motivation for the study actually lies elsewhere, and that's what I'll now try to explain. So this is just for the non-physicists in the audience, I presume a few. So I'll just so I think it's sort of fair to say that 20th century theoretical physics has stood on 2 pillars, and these are general relativity and quantum field theory. These are 2 big frameworks. I mean, there are 2 real pillars because there are frameworks which encompass a wide variety of things, and general theory of relativity for the non-physicists is a theory of gravity which has given us our most successful description of the cosmos and its evolution on the very largest scales. And quantum field theory, on the other hand, has captured the physics at the very smallest scales, and as we heard in the previous talk from Subir and so on, it's one of the mainstays of condensed matter physics and also statistical mechanics, etc. So it's also a very powerful framework. And what in recent years string theory has done, it indicates that there's a very profound, previously unsuspected link between these very different and intensely studied subjects. These are almost a century old. I mean, general relativity, we are celebrating the centenary this year. So string theory has indicated that these subjects that have been very well studied on their own, there are unsuspected, very new links between these subjects. And so in some sense, it makes verifiable or falsifiable statements or predictions about structures that pre-existed string theory. And I can't overemphasize how non-trivial this is. So this is, I mean, when people talk about falsifiability and so on, it's in some sense being falsified or verified, whatever, every day by the calculations that people are doing, which, so let me try to sort of indicate what this link is, this link between these two subjects, and this goes to, it connects to something that Subir was mentioning. So, so about 18 years ago, Juan Maldacena made a very precise proposal for the quantum behavior of gravity in a very large class of space-time. So, so the quantum behavior of gravity is, of course, a very the long-standing question and one of the central issues that string theory is addressing. So, but Maldacena made a precise proposal for a class of space-times which you can sort of depict in this hyperbolic fashion of Escher, and these are the things that the ADS space-times that cropped up in Subir's lectures, anti-de Sitter space-times. This is a sort of a caricature of a three-dimensional anti-de Sitter space-time, which will actually play a role in what I'll have to say later. So this vertical direction is the time direction, and these Escher drawings sort of indicate the hyperbolic nature of the spatial slices. So this is a sort of a cartoon of anti-de Sitter space-time, and what Maldacena proposed was that gravity, or more generally string theories in these anti-de Sitter space-times are equivalent to the quantum gravity, or just the behavior of gravity in these space-times can be equivalently described by a quantum field theory on the boundary of this space-time, which in this case would be the sort of two-dimensional cylinder, which is the surface of this solid three-dimensional ADS that you see over here. So this comes with a certain dictionary between the observables of the bulk and the boundary. So the bulk being the gravitational theory in this anti-de Sitter space, and the boundary being the quantum field theory living on the in this one lower dimension. And because of this fact that that the quantum field theory in one lower dimension captures physics of the interior of this higher dimensional gravitational theory, this is called the holographic sort of a connection. And so this is very remarkable because, as I said, it links quantum field theory and gravity, these two big pillars of 20th century theoretical physics. It translates non-trivial questions of quantum field theory to questions of gravity, and in very unexpected ways. So the answer to a very difficult question of quantum field theory, I'd say strong coupling, gets translated to a question in classical gravity. So this is, in fact, it reveals various surprising things, that there's some kind of universality in quantum field theories at strong coupling, and I believe that it's going to be it's already driven a lot of theory in this century and is going to continue. So this is the sort of the broad context, and so while we have this conjecture, we have many instances of this conjecture, very well tested and verified. We still, in a sense, lack an understanding of what is really at the root of this connection. What really makes this connection work, and so in such a situation, one time-tested strategy in physics is to sort of find simple, tractable examples which capture some of the essential features, maybe throwing away a lot of features, but capturing in some ways the core, and using these examples and the transparency of these examples to sort of try to decipher this correspondence. And that's what I'll focus on in this talk. I'll sort of give a broad brush sketch of one such example and what we sort of learn from it. And we already learn some important things, because it's also important to learn what's inessential. I mean, when you throw out things and see things work, then you realize that certain features are inessential. And you already see, and we'll see that many things which are often sort of in folklore believed to be essential are not really essential. Supersymmetry, for instance, which is often I mean, it's believed, people often make the statement that all these dualities use supersymmetry. That's not necessarily true. Yang-Mills type gauge theories are also, that's a particular kind of gauge theories. It's not necessary that it be of that kind. It's also not necessary that the gravitational theory be purely of Einstein type. So these are all features which in many of the examples do occur, but they are not essential for the connection. So we'll try to see we'll try to see this example in which you sort of go beyond some of these sort of features. I mentioned that it's not Einstein type gravity. The type of gravity that enters here is the theory of gravity that enters here is a somewhat unfamiliar one, even to many theoretical physicists. In anti-de Sitter space, actually, it turns out that there are certain classical, at least classical theories of gravity, which are intermediate in complexity between Einstein theory and string theory. So string theory, of course, is something which is an enormous sort of enhancement of Einstein theory involving an infinite number of additional states. But there's something intermediate, and this is the theory constructed by Vasiliev. And these have a single tower of higher spin fields. So a higher spin field is basically, for the physicist or the mathematician, it's a sort of a symmetric rank S tensor. So they have a single tower of these higher spin fields. You can think of them as sort of massless gauge fields, in addition to the spin S, this S equal to 2 case, which is the graviton. And this is unlike string theory, in which there are higher spin fields, but firstly their number grows exponentially, and they are usually massive. So in the Vasiliev theory, you have a finite number of fields at a given spin, and so it doesn't grow, the number doesn't grow as you increase the spin. So the Vasiliev theory has much more than the Einstein gravity, but it has not an exponentially larger set. But these higher spin fields come with a sort of a very large set of gauge invariances, just like Einstein's theory has the diffeomorphisms as the gauge symmetry. These theories have an infinite set of such gauge invariances, generalizing Einstein's diffeomorphism, and these typically are at the linearized level. These gauge invariances look something like this, but I should stress this is only the linearized form of the gauge symmetry. At the nonlinear level, these are it's much more complicated. But roughly you can see that this, for S equal to 2, this would have been the linearized diffeomorphism, but these are more general theories. So these Vasiliev theories with these nonlinear gauge invariances very tightly constrain the structure of equations of motion of these fields, and the set of equations actually was constructed after almost 10 years of work by Vasiliev, and it's a very intricate set of equations which I won't even tell you in general, but in 3 dimensions. So in 3-dimensional anti-de Sitter space, it takes on a relatively simple form, which you can sort of write in a very in just one line. It's what is called the Chern-Simons form for mathematicians. It's the Chern-Simons equations of motion, which is simpler than the Yang-Mills equations of motion. It's dA plus A wedge A equal to 0. So this so this gauge field A is related to the higher spin gauge fields that I wrote down earlier in the previous slide. These gauge fields here take values in a sort of what you might call a higher spin algebra, a much bigger Lie algebra. And in addition to these higher spin fields, which are gauge fields, you can also have matter, but the matter is very constrained. They can only take, it takes a very specific form. Typically, it's sort of, in the simplest case, it's just scalar matter, and the mass and other things are sort of fixed by the gauge symmetry. So it's a very high, the point I want to get across is that it's a very highly constrained system of equations, and but it's a well-defined classical, consistent classical theory, so you have these consistent theories of gravity on anti-de Sitter space. You can ask, is there a quantum field theory capturing these, is there a quantum field theory that captures these classical gravity theories in the sort of holographic way that I described? The proposal is, in the simplest case, the proposal with my collaborator Matthias Gabadil here is that the simplest Vasiliev theories in three-dimensional anti-de Sitter space that have duals which are interacting two-dimensional quantum field theories, so it's always one lower dimension. So the quantum field theories here are two-dimensional quantum field theories, but they are a class of quantum field theories which are actually by now in almost every theorist's toolkit, because they belong to a family of so-called two-dimensional conformal field theories, which are in some ways the simplest you can have. They are the so-called minimal model coset CFTs for the experts, but these are models which describe statistical mechanical systems at phase transitions. Example, the Ising model, the two-dimensional Ising model, for instance, and its generalization. So the class of two-dimensional quantum field theories that are being conjectured as dual to these Vasiliev theories are a very familiar set of quantum field theories. Moreover, there's a family of these CFTs, these quantum field theories, which are labeled by an integer n, and which sort of which is a measure of the number of degrees of freedom of the system. And the surprising thing is that these admit a large n limit which behaves classically in many ways. And this is along the lines of the classical behavior of the large n limit of many of the other quantum field theories that appear in these Maldacena conjectures, but it was sort of unexplored in this context earlier. These theories, as I said earlier, have no supersymmetry, but they have something else. They have additional conserved charges or additional conserved currents which carry higher spin. So the spin 2 energy momentum tensor, which measures the energy and momentum densities in a quantum field theory, is something common to all quantum field theories, but very few quantum field theories have conserved currents, which certainly interacting quantum field theories have conserved currents which carry spin higher than 2, but these minimal model CFTs are an exception in doing so, and it's this symmetry which is sometimes called the W symmetry, which matches with the higher spin gauge invariance of the bulk Vasiliev theory. So this three-dimensional Vasiliev theory had a very large gauge symmetry involving higher spin fields, and it's precisely these higher spin conserved currents of these two-dimensional CFTs which agrees with these with this higher spin Vasiliev theory. But we can, of course, go more than just talk about the symmetries. these quantum field theories are solvable. They are actually, you can actually calculate a number of things. For instance, the exact spectrum of states and many correlation functions. So you can actually make very explicit checks in the case of this in this model, and that's one of the. So this was one of the things we were looking for. We were looking for simple, tractable models in which you could say things very explicitly while still being fairly non-trivial, and in some ways these models have that feature. So just to sort of give you a taste of that, you can match, for instance, the states and in many cases the correlation functions in this between this quantum field theory and the gravity theory in the anti de Sitter space. So for instance, you can write down in the bulk theory, that means the Vasiliev three-dimensional theory, you can write down the generating function for all the states. So these Q and Q bars are just, if you wish, if you're mathematically minded, it's just the expansion parameter for your formal generating function of the states, but for a physicist, these are essentially the chemical potentials associated to the temperature and the momentum or angular momentum. So to energy and momentum. So this is just what you would call, a physicist would call the partition function. So this the bulk partition function can be computed in the semi-classical limit in an explicit way. There's a sort of a classical piece, and then there are pieces which are basically counting the states of the theory. This has several components. The first is a piece which counts the contributions from all the higher spin fields. So there you see a contribution from s equal to 2 to infinity. So these are all the higher spin fields from 2 to infinity. And each of them have a particular, there's a contribution from each of them. And this is a sort of a nice function called the McMahon function. And then there's a piece from the scalar field that I said you could couple to the Vasiliev theory, and there's a contribution from that. The parameter h is related to the parameter lambda that really defines your Vasiliev theory. There's a one parameter lambda that defines your gauge algebra, and this is so this is the parameter that enters over here. So it corresponds to the mass of the scalar. So this is the generating function, as I said, for what you could call the perturbative states of the Vasiliev theory on the three-dimensional anti de Sitter space. And you can try to compare this contribution to the corresponding states in the two-dimensional CFT, which also you can write down in a fairly explicit way, actually for the general case, without taking the large n limit or anything. You can write down the general form for this for the contribution to the partition function from a set of so-called primaries labeled by a representation of SUN. The general primaries are labeled by two representations, but the ones corresponding to the perturbative states have one of the representation labels set to 0. So these contributions are known very explicitly. They take up just to show that they're known very explicitly, never mind what all the symbols really stand for. But it's a generating function, a Q expansion with various coefficients which are known explicitly. So this, as I said, is for any n, and actually there is a parameter p in these theories that enters, for instance, over here. But if you take these generating functions and you take their large n limit with an appropriate scaling, keeping this this combination fixed, it's what Toft originally introduced as in gauge theories and Yang-Mills theories as the appropriate scaling limit to take the large n limit. If you take this limit, keeping this fixed, this answer, which doesn't look anything like the answer in the previous transparency actually matches. And so that's an example of how there's some remarkable simplification of these two-dimensional CFTs or quantum field theories in the large N limit, and they are captured by a much, in some sense, a simpler theory, well, in some sense simpler, some sense more complicated theory in the bulk, the Vasiliev theory. This was one example. There are correlation functions. There are new black holes in this Vasiliev theory, and their entropy can be accounted for by states of the CFT. There are recent computations for the entanglement entropy. With Subir, this motivated us to look for a toy model for some strange metal in 1+1 dimensions. It's an example of the interdisciplinarity, if you wish, of the subject. But I think the general lesson is that it shows that holography works beautifully even for non-supersymmetric theories. But having learned that lesson, there's no reason to not generalize to supersymmetric examples and try to connect to string theory examples of duality, because there are string theories on three-dimensional antidesitter space, which are dual to two-dimensional quantum field theories. As I said earlier, string theories are much more elaborate than the Vasiliev theories, but so you can try to see what's the relation between these simpler sort of dualities which involve only a Vasiliev theory and the more complicated string theories. So that's one question you might try to so you might try to now use these simpler holographic dualities to learn something about string theory. And indeed, that was one reason how string theorists came to study the Vasiliev theory, because the Vasiliev theories are believed to be a subsector of the string theory in a certain so-called tensionless limit, where a lot of states become massless, so it can only be a subsector because, as I said, it has far fewer states. In the particular case of a string theory involved on three-dimensional antidesitter space times various other factors, you can try to identify this subsector, and indeed you find that in the two-dimensional CFT, which is believed to be dual to this string theory on this background, the Vasiliev theory does sit as a subsector, sort of a consistent subsector of the full string spectrum. But what's more interesting in a sense is that you can organize the full string spectrum at this tensionless point in terms of representations of the higher spin symmetry. So there are now, the string theory has many more states, as I said, exponentially larger number of states. You can try to organize all of them in terms of this higher spin symmetry, and you find that indeed that's possible. And in particular, you can look at the massless states in this tensionless limit and see whether they fit into higher spin, they fit into higher spin symmetry multiplets. And indeed they do. All the massless states or the corresponding conserved currents can be viewed in terms of the higher spin representations of the Vasiliev symmetry generators. But there are many more in this limit in the string theory than even at the massless level. There are many more states in this vacuum compared to the Vasiliev theory, and this is a signature of a very large unbroken sort of a stringy symmetry whose sort of which had been conjectured by, among other people, David, that there's a phase where you have a large unbroken stringy symmetry, and you indeed see that there is this stringy symmetry, but what's very interesting, what we are excited about is that viewed from the lens of the higher spin theory, these stringy symmetries form a very novel structure. The generators of the stringy symmetry form a very novel structure. So if you think of the Vasiliev generators as a subset of this of the full symmetry generators. They form, you can arrange them in sort of one column, this vertical column to the left, but there are an infinite number of others, in fact, an infinite number of columns. You can arrange all the others in representations. These are these other columns. But when you do that, you notice that there's actually a bonus higher spin symmetry which acts across the columns. So there's an extra higher symmetry which acts in a sense horizontally, whereas the original one acted vertically. And these two higher spin symmetries in some sense generate an exponentially larger algebra, this whole stringy symmetry algebra, which we call the higher spin square. So there's a sort of a very neat structure when viewed from the lens of these higher spin symmetries for the full stringy symmetry. And this encourages us because the Vasiliev equations, as I said at the beginning, were completely determined by the higher spin symmetries. They were very constrained by the gauge invariances. And string theory is also, you believe, unique, though it's hard to put your finger on how exactly that is determined, how that uniqueness is determined. So you can ask, is it completely determined by symmetry, just like Vasiliev theory was completely determined by the symmetry? Is something like this higher spin square sufficiently constraining that it sort of constrains the full spectrum and perhaps interactions of the theory? We don't yet know. We would like to think that there's a sort of fighting chance that it is so. One small encouraging sign we've seen recently is that a very large set of states of the full string spectrum, other than the now I'm talking of the massive string spectrum, combines into a sort of a single minimal representation of this higher spin square of the full stringy symmetry. So it's what you would, for the sort of the string theorists, it's the entire untwisted sector of the symmetric product CFT. So this representation is analogous to the scalar that we had in the Vasiliev theory in the earlier holographic example. And what we would really like to see is if the whole string spectrum can be sort of organized in terms of a very few representations of this bigger stringy symmetry algebra. So let me just sum up by reiterating some of the points. So the relation between quantum field theories and gravity or string theories is in some sense very deep, but it's ill understood. But you can already see the power of this connection in very simple toy models in revealing very unexpected features of theories that you thought you understood very well and had studied very well. And these examples have the virtue of being non-trivial and yet tractable. One might therefore, I hope, to use this to unravel the underlying mechanism, the nuts and bolts. But as I tried to tell you at the end, hopefully these examples also in turn feed back and may try to shed light on string theory.